Yes, and so you can actually see the recorded plenary talks at this website, which is great. So super quick reminder, make sure we're all on the same page, that what we're doing with radial velocity measurements or Doppler measurements is we're looking at measuring the radial velocity of the star. So we look from some distance and we see not a star, not a planet, but a spectrum. And that spectrum is shifting back and forth as the star is coming towards us or going away from us. And so over time we'll map out, based on the wavelength shift of the spectrum, a radial velocity. And we can use that, the orbital period with Kepler's law and the amplitude to derive the presence of an unseen planet orbiting another star. Okay, so there's a slight crisis, though, in this field. If you look at this nice plot that was put together by Hanno Rein, I started working in this field in the 1997, right? And so every year I could give a talk and say, we found more planets than the year before. And that was true up until about 2012, right? And when there was this dramatic turnover. And this is the result of a couple of things. First of all, the field was turned towards follow-up of transits, so that ate up some of the telescope time. But there was another thing going on, and that is that we hadn't really improved our radial velocity precision for a while. There had been lots of gains in the early days, and then we had kind of plateaued out. So at the EPRV meeting, sorry, Courtney, you'll have to see this again, I put up this fun plot, which I first saw by Lars Buchheve. And basically the idea is that our radial velocity error there's an error budget, right? There are several terms that contribute to the uncertainty in our measurement, and it's the quadrature, sum of these terms that really comprises the single value which we call our radial velocity error. And we know what some of these errors are, and we know their magnitudes now. And I suspect that what's happened is that the magnitude of several error terms they're similar, right? So we're doing, based on the sort of detector technology, the wavelength calibration, the stellar noise, our understanding of the PSF, which distorts the spectrum, our analysis tools, they all contribute at some small level. And right now, if we tap down on one of these nails, we're not going to improve our velocity error budget. They all have to go down, right? And so that is the job that we were discussing at this PRV workshop, is how we're going to tap everything down. And the important thing to remember is that even if we tap down everything except one last object, right? If there's just this one thing left, then we'll be, what's the word I'm looking for?
Screwed.
Yeah, screwed. We'll be screwed. Okay, right. And I suspect that this last term is stellar activity. And so...
These are not nails in the coffin,
right? Funny guy. And so our job is to find the right tools to drive down the precision. Yeah. And so I want to tell you about some of the things that I learned at this meeting, which both scare me and encourage me. The first thing that we did was we took the pulse of the community with what I call the state of the art. And so this was the first time that I know of that we've gotten people from all of these major, planet surveys to come together and to show us what they're really getting in terms of radial velocity precision. And the results are pretty interesting. So we asked for a very specific format where they show us a histogram of their internal errors, a histogram of the RMS, and also a plot of how the errors drop down with increasing signal to noise. So we put together this table, but I'll show you the plots, right, which are more revealing. So this is kind of cool because in the 90s, when I was working at Lick Observatory, we were getting 3 meters a second in terms of our Doppler precision. I'm pretty proud of it. And here's, in that same era, sort of what McDonald Observatory was doing. And I would say that we don't have data from, what was it at the time, Coralie in the 90s? Coralie, LED, right? But LED had a similar error distribution. And so there's been considerable effort that's been put into this field for some time. And it doesn't matter about the details, I think, of the individual surveys, but what you can do is I tried very carefully to line up 0 to 10 meters per second for the mean radial velocity error that people are getting. And you can see that there's the red dots go along 1 meter per second. And so what looks, to me, it looks pretty encouraging that there are, definitely HARPs, which uses a different instrument and a different wavelength calibrator, is edging down in terms of its precision, or edging up. I never know quite what to say. And some of the other techniques, I think, which use iodine cells, are maybe drifting a little bit to the side. But come on, we're all just about at 1 meter per second precision. And so is that good enough? It's not if you want to find an Earth version 2.0. Because the reflex velocity that the Earth exerts on the sun is 9 centimeters per second, and you have to watch over 1 full year to be able to detect that signal. And probably for a tiny signal like that, you're going to have to look longer. And at that point, you have the complication of multiple planets coming in, right? And so this is a very complicated problem. But the question is whether or not in the next decade we can improve the precision that we've had. You saw it go from the 1990s, to 2010, basically, from 10 meters per second to 1 meter per second. How far can we go in the next decade in terms of pushing this down to 10 centimeters per second or below? And so I'm going to outline some of the this is work of other people that I'm actually telling you about. But the big problems, we broke the workshop down into 3 days. We focused 1 day on instrumentation, another day on data analysis techniques, and then the third day really focused on separating stellar photospheric noise. I always feel guilty saying it's noise because that's somebody else's signal, but the signals that arise from the photosphere of the star rather than center of mass velocity variations, the thing that I think is probably going to be the hardest one to drill down. The great thing is that we had people from all these different disciplines looking at the problem. And so that turned out to be pretty interesting in terms of the discussion that we had. And we also had some sponsorship and representation from industry. So we got Minlo Systems to come and present their latest on their laser frequency combs. Fibertech Optica came and talked about their fibers, exotic fibers and fiber scrambling. And E2V came and talked about the detectors. So I'll show you some of the scary things that came out of all of that. Andy Sayorgi and Suvrith Mahadevan gave the opening talk, and so they were like a tag team. One would talk for 5 minutes, and then the other one would come out, which kept it lively. They have very different styles. They talked about the idea, sort of a general overview. There are two different basic types of spectrographs that can be used to search for exoplanets. One is a classical design. You have lots of optics, and it's big, right? But you understand it well, right? And the other is a new idea which uses anamorphic lenses to reshape the pupil as the light's going through the spectrograph. And the scary thing is you can no longer test one lens in isolation. You have to put the whole thing together and then see if it works, right? And so this is the design. And since Francesco Pepe is so awesome, I have no doubt that he'll make it work for espresso. And then other designs like GClef are sticking with a more classical design. Suvrith, among other things, talked about the fact that we've really got to improve the instability of our instruments. And that means, putting things in not just a HARPS-like enclosure, which is a vacuum enclosure, and it's very stable, and it's put inside of a little box. And apparently, if you're in Geneva and you open that box, you are in big trouble. But if you stabilize the pressure, one of the things that I thought erroneously was that it doesn't matter what the pressure is as long as it isn't changing. That's not quite true. So if you stabilize the pressure to 10 to the minus 2, then you minimize the refractive index variations inside your spectrograph. But what you really want to do is knock it down to 10 to the minus 7 torr. And at that point, you've actually stopped the molecular transfer, right? You've taken out the molecules, the things that are conducting energy in the system. And now you have a system that's radiatively coupled, and it's extremely stable. So this is something that we see happening in the infrared, right, where they have very sophisticated coolers and getters and pull out all of the molecules and everything. And it's something we need to start thinking about for the optical. And then with this, it'll be no problem to get temperature stability of sort of at the millikelvin level. So there are a lot of tractable problems, and there are some that are harder. So some of the challenges that we face in terms of precision can actually be calibrated out if you have extremely high wavelength calibration. You can monitor the thermoelastic distortions, right, that cause settling in the spectrograph and shift your spectrum around. You can monitor the, whoops, wow, that was really, oh, no, that wasn't so far. Okay, you can monitor the mechanical stability and the pressure. And you can look for things like CCD stitching errors, which I think the astronomical community did not even know existed like a year ago. And I'll show you a picture so that shows you we should be a little scared. But there are things that you can't calibrate out, no matter how precise you make your instrument. And I think that's where we really need to focus our effort in the coming few years. The Bary-centric errors, so I'll give you an update on those. Telluric contamination, software fitting errors, micro vibrations of your instrument will be, can be systematic. Detector errors, so these can be intra-pixel QE variations, so not just from pixel to pixel, but just across a pixel. Whether there's detector heating on readout, flux-dependent charge transfer efficiency errors, you know, all of these things. This is going to be a huge effort in the next few years. Stray light, we can't calibrate it out, so you want to design an instrument that minimizes the stray light. And then the focus and the guiding errors. If the light is shifting around, if the light intensity distribution is shifting around on your optics inside the spectrograph, you are getting a spectrum that's changing. It's changing its shape. So I decided one of the things that I was going to leave out of the presentation today, because it's just too big, is the discussion that we had on wavelength calibration, a fairly extensive discussion. Bottom line is, thorium argon lamps were great, you know, for a while, but the lamps age, they're not stable, there are all sorts of problems. Iodine cell is, wow, just what you'd want to use if you're using an instrument that's, you know, not stabilized. It's a general purpose instrument. But there's degeneracies in modeling the iodine and the forward modeling technique. We don't really know the underlying iodine spectrum as well as we thought we knew it. We can't guarantee that it won't change ever. We've seen changes at Lick Observatory. And so there's no question that the community is devoting considerable effort into some new kinds of wavelength calibrators, and they all have one thing in common. They're all emission combs. Okay, so there's the laser frequency comb. There are line referenced electro-optical frequency combs. There are etalons, there are Fabry-Perots, and if you wanted to ask questions at the end, I could come back and touch on any of these. But the bottom line is, I think, you know, Menlo Systems has pushed pretty hard to get out what they think of as an appliance-grade laser frequency comb. I think it's still TBD how robust that system will be, but they're installing them at observatories, and for basically $750,000, which is, you know, it's a lot of money, but it's not necessarily a showstopper if you're building a $10 million instrument. So for $750,000, you can buy a laser frequency comb that will work from 400 nanometers beyond 1 micron. And it's locked to a GPS signal, and you know exactly what the wavelength of every single line is in that frequency comb. There's some work that's being done actually here. Chaz Beichman is working on it using these line referenced EOFCs. The etalons, the Geneva team is investing some time in. My team is working on a tunable Fabry-Perot, which we're excited about. So we'll see what happens. And again, it's such a huge topic, it deserves a whole talk in itself. Okay, so here's some of the things that I learned, which were a little scary. I sort of had heard about these stitching errors, but Paul Jordan from E2V explained that when they make a CCD, they are basically using a lithography process, and the camera is projecting the pixels onto a silicon substrate. Okay, so the field of view of the camera, this field of view has to be incredibly flat. By the time you get over to the edges, you start to have curvature and magnification in your field, which you don't want because it changes the pixel sizes, it causes distortions. And so the pixel blocks are limited to 512 by 512 pixels, period. Whatever CCD you buy, it's made up of these little subunits of CCD blocks. And when they're laid down, they have right now, E2V has, okay, you scared me, I thought my time was up. Okay, when E2V has two machines that lay down the CCDs, one of them was called their Ultratech Stepper, and it resulted in errors of 250 nanometers between the 15 micron pixels, right, the sizes on these blocks. So they recently upgraded to a Nikon system, which has 90 nanometer errors. Okay. Now, the cameras are put on, they have a stepper motor that operates them and shifts them around. And so the error between one block and the next block is not correlated, right? Everything is tied to the position, a 0 point in the stepper motor. And so the errors in laying down these CCD blocks are random. And they look kind of like that, which is, I mean, it's exaggerated so we can see, but it's pretty scary. And so if you are taking a spectrum and you look at, you're going across here, your spectrum is going across here, and you cross one of these boundaries, you're going to get a jump, you know, positive or negative in the radial velocities, because you're not measuring a continuous 15 micron pixel all across the device. All of a sudden, the position changed and you didn't really know it. We didn't know about these things until we started using laser frequency combs, which suddenly said, wait, why is it that after every 512 pixels, I see this big jump in the radial velocities? And they went back to the manufacturers who said, oh, yeah, that's because of the stitching process that I guess we didn't tell you about. So I think I'm telling you this story because it highlights the need to close the loop and to bring in industry, you know, to solving the problems, for bringing people in the telecom community. There's a lot they can do. The CCDs are, you know, they are flawed at some level. So what you're looking at here is a close-up of some silicon, and this is Z-band. So in the near infrared fringing, a level of 2%, so your spectrum is rolling across there, right? If that doesn't flat field out perfectly, which it won't, then you're going to be left with some residual errors, and that's hard to characterize. Here is some fringing on a 70 micron device, CCD. This one is on a, what is it, 15 micron thick E2V CCD. So this is the middle one is a deep depletion device. And then in the ultraviolet, so these are, Z is near infrared, of course, but you don't improve in the, here's what things look like in the near UV. So these are, again, these are flaws, imperfections in the detectors. Some people are worried that detectors may actually set the floor in terms of our RV threshold. I don't know. Here's another scary thing. We're looking under the hood, and Lars Buchheve showed these data. So he looked at the HARPS data, and he found that when he looked at used a thorium argon, which was, you know, it takes a second or something for the thorium argon exposure. He tracked out a change essentially in the velocity. This is a shift of the line. So we use, you know, a shift in wavelength and a velocity shift interchangeably. So he sees this velocity shift in the thorium argon, right? And he said, what could that be due to? It's like roughly every few minutes. You can see time 0, 5, 10, 15 minutes here. It's going back and forth. And he discovered that inside of the Dewar, there's a cold plate, right, which is being cooled so that it can radiate and cool the detector. And the cold plate was cycling, had thermal cycling that was really tightly correlated with this variation. Okay, so So this is not the detector that's changing in any way. This is the cold plate, which, as the temperature changes, the thermal coefficients that control the little wires that hold the CCD, are essentially elastic at this level. And so there's a little bit of tilt that's being introduced. All right, so this tells us that we need to cycle the temperature on the cold plate faster, or we need to somehow smooth this out. Alternatively, what Lars did was he took longer exposures. So if his thorium-argon exposures lasted for a minute or two, then he could beat down this oscillation in the same way we try and beat down other noise sources like P-mode oscillations. But that was amazing and something that I'm not sure that people had really known about.
What was that temperature roughly? Temperature change, was that a millikelvin?
Yeah, millikelvin. It's tiny on the cold plate. Yeah. So the detector was totally stable, but the cold plate was cycling. Okay.
It shows it to be several degrees, right?
It looks like it's, yeah.
Sorry.
It says it's
Capacitive temperature.
centigrade.
This is his slide, so let me double check because that does seem like a lot. 4 degrees. But maybe that's okay. Maybe to keep the detector stable at the millikelvin level, that this really is cycling by a few degrees. Yeah.
Those, by the way, the temperature drifts we sort of see inside the nurse spec, which is not temperature stabilized, except right on the detector.
Right. Yeah. We're looking under the hood, and we're looking at every single detail with much more care than has ever been done before. There's also been a lot of work, and I consider this to be an almost solved problem. A lot of work that's been done on fiber scrambling. If you take a spectrum, then every spectral line, every pixel at the camera of your is re-imaging the slit. And so if you're shining the light on the slit right in the middle, then you get, your PSF is nicely, the point spread function of the optics is nicely centered about, some 0 point. But if the guider, or let's say the guider, TV guide camera, causes the slit or the star to move over to one edge of the slit or the other, then the PSF will cause the spectrum to shift around on your detector. So that's a velocity shift. That's an error that's very systematic and very bad. And so what we're doing now is using fibers. So we input now the starlight into a fiber, and no matter how we dump the light into the fiber, we more or less get a stable PSF, a stable spectrum. Not completely stable, because some of the work by Gabor has shown that here, what you see in this column is the fiber, and then they're putting the light in, shining the light. So here there's perfect guiding, the light's going right down the middle of the fiber. Here they're stepping the input illumination off from the center. And now they're asking, is the output of the fiber completely decoupled? Is it completely independent from how I put the light in? And if you looked across here, you would say no. At all of those wavelengths, there's definite structure that's changing depending on how the light's going in. This is a much lower level than what happens with the slit-fed spectrograph, but it still is a worry. And so, just scrambling isn't enough. We've been trying exotic fibers and now double fiber scramblers and agitating the fiber. And I could go on and on about this because my team's been working quite a bit on it. But the one thing that came out that was a new idea for me, which actually shouldn't have been, is that a lot of us want to not just use a fiber, but we want to slice the fiber because we are very greedy. We want very high resolution. So if we could, we'd choose a really tiny fiber, but that's not, we can't get all the light into it. So let's just slice it, right? I slice this with optics in half, and then I stack these little half moons here, right? And then off it goes to the spectrograph. All right. So what was happening in this case is that there was modal noise, right? There's speckle pattern, but those speckles, there's a conservation of energy that's being conserved, and my spectrograph is capturing that. When I slice the image, that might not be happening. And so here, I think, there's a movie. That's running, yeah, showing the speckle pattern. So if you slice this, then you're slicing the mode. So let's say you have more power here. This could happen if your connector had some flaw in it, your connector on your fiber, right? Then you would be getting a larger center of mass shift. And so what we have to do is break down the contrast of these fibers. And I would say what we want to do is when we dump the light back into the spectrograph, we want to put it into a rectangular fiber so that it's finally well scrambled before it goes to the spectrograph. Okay. All right, in the barycentric corrections, I'm going to tell you sort of quickly that there's this beautiful paper by Jason Wright and Jason Eastman that came out about a year ago on barycentric corrections. They looked in incredible detail at everything that goes into the recipe for calculating the barycentric shift correctly. And I thought this is it. This is like, you know, the paper forever. And yet they discovered in the interim, in the last few months actually, that a lot of us are not actually doing the flux-weighted centroid correctly. We calculate a flux-weighted midpoint for our observations, we save that time, and then we apply the barycentric correction based on that. In fact, we should be recording every pulse of light. For the barycentric correction, we're sampling at, 10 hertz maybe. So we should be collecting every point, getting a barycentric correction for that point, and then combining it. And the sort of example that they gave is that if you have 100% flux and then a cloud rolls in, you have 0 flux and 100% flux, then your midpoint will be in between those, but it actually will be off by something like 30 to 50 centimeters per second. So no one's been implementing this correctly, not us, not the Geneva team, nobody. So we all have these errors of about 30 to 50 meters per second from the barycentric correction. We talked a lot about microtellurics, so we all look at this kind of a plot and we say, man, things are so bad in the infrared. I'm sure glad I am not working there. I'm really glad that I am an optical astronomer, because here from point 4 to point 8, okay, there's a little bit of stuff that creeps in, but it's really not bad. That's true on a scale like this, but if you look really carefully, there's a nice paper by Kuna et al., which shows that there are microtellurics, so these are at the level of up to a couple of percent, that go through the optical band. And I think we need to think carefully about how those are going to limit our precision once we're trying to get to 10 centimeters per second or less. Okay, on to day 2. This was the scariest day of all for me. This is when the statistics dudes got up and gave their talks, So Tom Laredo basically said there's a reproducibility crisis in science. Right now everybody's focusing on pharmaceuticals, right, the healthcare industry. But the truth is that if they looked at what we're doing in exoplanets, we would not survive the scrutiny that they would give to our data analysis techniques. Okay, we are really in trouble in the way that we think about it. And I'll show you. Here's some quotes from papers, right? This detection has a signal-to-noise ratio of 4 with an estimated upper limit on the false alarm probability of 1%. I read these sentences in every refereed paper on exoplanet detections, right? And so I'm like, oh God, what is he going to say that's bad about this? And so he goes through, the false alarm probability for the signal is rather high at a few percent. He said all of these statements are meaningless. All of these statements are incorrect. They reflect an incorrect understanding by astronomers of what an FAP is, false alarm probability. In fact, false alarm probability sounds like we know so much more than we do know. Stop calling it that. Just call it a p-value, which reflects this sort of murkiness. And here's what the p-value really means, okay? A p-value means in a world with absolutely no exoplanets, with a threshold set, so we wrongly claim to detect planets 100 times p% of the time, this is the p-value, this data would be judged to be a detection. Okay, so that's not very satisfying when you put it like that, and yet that's what we're doing, okay? P-values are not statements about the detected signals, they're statements about the ensemble of possible null-generated signals in our data sets. So I had to listen to his talk 3 times to figure out what he's saying and why we've been so wrong for so long. Then the other scary thing is he said, you know, on the KS test, okay, so this is another thing that we're doing wrong. The KS test is incorrectly used in over 500 refereed papers each year in the astronomical literature. Okay, it assumes that there's a continuous underlying distribution to the two samples. And even if that's true, it's actually not very sensitive to finding the distance between the populations. There are other tests that we should be using. So now all I know is that I'm scared and I'm not quite sure what to do about it, but maybe that's okay. Maybe being scared is the first step. David Hogg then got up and he said, if you guys are using chi-squared minimization, you could be doing something a lot better. All right. And if you're willing to assume that things are Gaussian, you can marginalize over thousands of model parameters, you know, efficiently using just linear algebra. My eyes are rolling to the back of my head, you know. And then he says, suck it up. All right, you cannot do precision spectroscopy without fancy math. You better partner with some statistically savvy colleagues. Okay, it's tricky for RVs because most of his work with Danforth and Mackey was done on the Kepler data where you have transit signals, but a lot of the time you have data that doesn't have signals in it, right? So you can learn about the underlying noise. For radial velocities, that's a problem. And that can change. If a 6-planet system becomes a 7-planet system, then all of a sudden it changes our beliefs about what the underlying noise is. Okay. And then Eric Ford said, you know, in the 1990s, you old guys used frequentist approach, okay, because you were just trying to disprove the null hypothesis, which is that stars don't have planets. We now know that's ridiculous. All right, you need to start using Bayesian approaches. You need to collaborate with people to build on strengths of our community. All right, we can't all be experts in these techniques. You know, he gave a whole bunch of, Eric is great about giving very specific advice. You do 1, 2, 3, 4, and here's what you don't do, right? And so his talk is outstanding, and you guys should definitely listen to that. I want to finish up with just a few examples from the third day now that began to talk about the stellar noise. Because in our community, it's a wide-held belief that we are limited by stellar noise, right? And that's true. For the instruments that we use that have the resolution that we're using, we can't tell the difference between stellar noise, right, photospheric velocities, and a center of mass velocity for the star. We know that that's imprinted in the data. We know that the stellar noise, the stellar jitter, the photospheric velocities are imprinted on the data. That's why our velocities are scattering around. But it turns out that if you think about it carefully, they're not imprinted identically to a Doppler shift. And so the challenge for our community is to figure out whether or not in the next 5 years we can learn to distinguish those photospheric velocities from the center of mass velocities. And if we can, then we can get down to, you know, I don't know how high precision. So we heard a series of talks about this, you know, the importance of having a very stable spectrograph for being able to see the stellar activity signals. And then one of the most exciting talks, at least for me, I have to go back and look at it again, was Thorsten Carroll, who said, you know, there's information that we can use to disentangle the planet activity signals. He said, for a slowly rotating star, let's say it has a spot on it, then nobody expects that you can disentangle that signal, right? Because it's in the core of the line, and that line is broadened by all of the natural processes, that Doppler broadening and thermal broadening, that broaden a stellar line. And so all you see is a slight change in the flux of the line. So that doesn't work. But he said, when I do a principal component analysis of the cross-correlation function, it turns out that the eigenvalues from the PCA actually show signatures that correlate with noise. So this is a huge breakthrough. And there were other talks like this. I mean, Rebecca Dawson told us about the importance of looking at aliasing in stellar activity. Enrique Herrero told us, you know, ideas for disentangling Doppler shifts from stellar activity based on the wavelength information and the shapes of the line profiles. Artie Hotze said, yeah, but come on. He's one of the old dudes like me. You know, frequentist methods can be useful for identifying cases when there's something funny going on. I'll show you some work that Matt Shiger, my student, has been doing as part of his PhD thesis. We used the MOST satellite and Chiron spectrograph to look at Epsilon Eridani. And here you see the radial velocities from Epsiri. They're varying because Epsiri is a K2 star that's heavily spotted, and it has a rotation period of 11 days. And here you see the MOST photometry. And so the gold is a model fit to these two data sets. And solving simultaneously, Matt comes up with a picture like this, right, for where the spots are located in a big MC calculation. But that's not the exciting part of this story. The exciting part is that he said, wow, the H-alpha emission is also correlated with the photometry, very nicely. So here you see the MOST in blue and his H-alpha measurement in gold. And if I use an HH prime method, which is like Suzanne Agrain's FF prime method, take the derivative, then I can figure out the correlation with the radial velocities. This is just one single line, H-alpha. There is a lot of information in the spectrum. And maybe if we use a PCA approach to trying to find and separate this underlying noise from the signal, we'll actually get there in the next few years. Okay, so the takeaway message is, I'll just be honest, I don't know if we're going to be able to reach 10 centimeter per second precision, which is what we need to detect Earth 2.0. But we have a lot of ideas to address the many challenges. And as scientists, we need to focus on the impossible. Okay, Malcolm was just saying this before, not just the things we know we can do, let's just reach and try and do something that we don't know if we can do. It's a little bit risky, right? The correct statement of the status of the field is this: we don't know that we cannot reach Earth 2.0 detecting radial velocity precision. Okay, so I'll leave it there. Yeah. This was a plea from, I'll repeat that question in my answer. So a plea from Eric Ford was that we record not just the spectra and not just the velocities and the time and the errors, but that we record everything. Because then somebody who's more clever can come along with, as they develop techniques and begin to use these as priors. I mean, David Hogg said, don't use a temperature probe and say that the temperature probe, tells me that there's this trend in the data and therefore I'm going to remove this trend in the data, because in his words, temperature probes suck. And so we should include the temperature, with a Bayesian uncertainty in our model, in our forward model. So everything needs to be rolled in. And we have to move past, where we are now and get to that point, I think. When people do the spot modeling with photometry and Doppler tomography sorts of efforts, then they always find that the spots are located near the poles. This is very common. And it's exactly the question I asked my student, wait, why is that spot on the pole? And is that, does that bear out in the literature? I mean, in some sense, I said, are you sure by putting the spot, closer to the pole, what you've done is you reduce the impact of the velocity? Are you sure that it's not degenerate with some other parameters? And so he has this massive Bayesian space that he explored, and that is, the best answer that came out. And whether it's right or what it means, I don't know.
Maybe it's physics, right?
Maybe it's physics, yeah. Exactly, which is a different spectral type than Epsiri and so forth. And this Epsiri is a younger star, and I think there's interesting physics there, and it would be good to explore that. Right. So just to capture Scott's two comments, the first comment was that he didn't quite hear that I had said that stellar noise was distinct from a Doppler shift, and therefore it's possible, that they can be separated out. I mean, I'm sorry that didn't come across. That's actually my main point in sort of trying to go through this, but maybe I understood it and didn't say it. And then the other point is that, this is a pretty cheap effort. When you look at, the 16-meter telescopes that NASA's talking about building and parking at the Earth-Moon Lagrange point, wow, it's really cheap. And so the more we can do to support, space missions, to be able to find the Earth and characterize the architecture of the planetary systems, the easier it will be in terms of the exoplanet requirements for those telescopes. Maybe you can get away with a slightly smaller aperture or something. Chaz? Okay, so NASA canceled the Space Interferometry mission in something like 2009. We were there. We were very saddened by that, and the justification that was given was that radial velocity is going to do it. Radial velocities will be able to reach this very high precision. And I think that didn't come from the US community, although I would say now that I would sort of join that chorus and say maybe we can do it. But it came from the progress that we were seeing from the Europeans, especially for working with HARPS, getting sub-meter per second precision, and the sense that maybe there was no limit in how low one could go. And so, maybe that's the reason they gave. I bet there were other reasons as well, that they wanted to bankroll the future spendings in that mission. And so but anyway, if we take that and we run with that, then what would the dream machine be that we would want to build to finally reach, 10 or 1 centimeter per second precision? And for me in the US, it's frustrating because, I see the Swiss National Science Foundation just invested more than $40 million in an effort just focused in Switzerland to push this. And we just I don't know if there's so much infighting in the US or what's going on, but we just can't seem to get traction within NSF or within NASA. It's always a little bit too little and too late. And so, given what we know, what we've learned here, I think that we can get there to very high precision, but to separate the noise from the center of mass velocities, we're going to need, I think, extremely high resolution. So unfortunately, we're building a machine, Express, which will go on the Discovery Channel telescope. It's a 4-meter telescope in Arizona. We're going for a resolution of 200,000. And so some people say that is stupid, that is a complete waste, because you completely resolve the stellar lines at 90,000, so why would you go to 200,000? That is very expensive in terms of the photons. And we say because sometimes you find things that you didn't expect to find when you sample things better than ever. And it was true for Kepler, right? The astroseismologists never expected to see signal at low frequencies, and when the mission just went on and on, they started to. So our hope is that, by building a machine where the spectral line has not just 4 or 5 or 6 pixels across it, but has 20 pixels across it, that will actually begin to resolve the details of the line profile variations, which creep in because of the photospheric velocities. Now, you have to add to that the wavelength dependence. Okay, so the stellar noise, the photospheric signals are stronger in the blue, because there tends to be more contrast between the photosphere and the dark spots than in the red. And it's different depending on what you're talking about in terms of stellar noise. But I think you also want to have incredibly broad wavelength calibration, or wavelength coverage. So those two things, really high resolution and really broad wavelength coverage, I think will get you there. And what it would cost is probably about $20 million for Keck.